Hello everyone, welcome back to Neural Network Lectures. In the previous video, we have discussed and implemented logical AND gate, OR gate, NOT gate, and NOR gate using McCulloch-Pitts model. Also, I have asked you to implement NAND gate as a homework. I hope that everyone did that. Okay. So, continuing from what we have left, in this video, we will be implementing XOR and XNOR gate using McCulloch-Pitts model. So, without wasting time, let's move on to that. As always, we will write the truth table first. Therefore, x1, x2, and output y. And the inputs are 0, 0, 0, 1, 1, 0, and 1, 1. So the corresponding outputs are 0, 1, 1, 0. Now we will write the expression for XOR gate. Y equal to x1 bar x2 plus x2 bar x1. I hope that everyone is familiar with this. Now we know the Boolean expression a dot a bar is equal to 0, right? Therefore, using the same logic, I will rewrite this equation. Y equal to x1 bar x2 plus x2 bar x1 plus x1 bar x1 plus x2 bar x2. See, these two terms are 0. Therefore, it doesn't change the equation. Now, using distributive law, I will write this as x1 bar plus x2 bar plus x2 into x1 bar plus x2 bar, which can again be written as x1 bar plus x2 bar into x1 plus x2, right? Now, using De Morgan's law, we know that a dot b the whole bar equal to a bar plus b bar. Using the same logic, we will write this part as x1 x2 the whole bar into x1 plus x2. Is it okay? So if we look into it, we have a NAND gate over here, we have an OR gate over here, and this total expression is ANDed, right? So we need NAND gate, OR gate, and AND gate to implement the XOR gate. Therefore, AND gate can be written as, remember the previous video? This is the AND gate, x1 plus x2 minus 1.5, x1 plus x2 minus 1.5, and we need OR gate, right? See, OR gate, and OR gate can be written as yk equal to x2 plus x1 minus 1. Therefore, OR equal to x1 plus x2 minus 1, right? Now what we need is NAND gate, and NAND gate can be, I hope that everyone did the homework, can be written as minus x1 minus x2 plus 1. Now we will try to implement this. Therefore, first we have 3 input nodes, right? One is x0 equal to 1, and this is x1, and this is x2. So first we will implement this OR gate. Okay, OR gate is x1 plus x2 minus 1. Therefore, we can write it as OR and x1, x2, where the weights are 1, 1, and the weight of the bias is minus 1, right? Now we will implement the NAND gate part. Okay, and this is the NAND linear summarizer for NAND gate. NAND gate is x1 is minus 1, x2 is minus 1, and the bias is 1. Okay, now what you have to do is take the AND of NAND and OR gate. Therefore, we take the AND gate, and therefore the weights are 1, 1, and we have a bias also, and the bias is minus 1.5. Therefore, this is minus 1.5. Now, if we fed this to an activation function phi of k, which is obviously the threshold function, we will get the output as XOR gate. Okay, thus we have implemented the XOR gate, and just study this carefully because this is a bit different from what we have implemented previously. Okay, now we will try to implement the XNOR gate. Before going on to that, I want all of you to pause the video and try it yourself. Then you can watch the video. That way you will be able to learn, right? Okay. In order to implement the XNOR gate also, proceeding as before, first we will write the truth table. x1, x2, and y. 0, 0, 0, 1, 1, 0, and 1, 1. And the outputs are 1, 0, 0, 1. Now, writing the Boolean expression for XNOR gate, y equal to x1 x2 plus x1 bar into x2 bar, right? Now, using De Morgan's law, you can again write this as x1 x2 plus x1 plus x2 the whole bar. So, we can see an AND gate over here. This is AND. We can see an NOR gate over here, and this is an OR gate, right? And in the previous video, we have derived the expression for AND gate as x1 plus x2 minus 1.5, OR gate as x1 plus x2 minus 1, and for NOR gate as x minus x1 minus x2 plus 0.5. Now we will try to implement this over here. Okay. So first we have the input nodes. These are the input nodes. This is x0, which is the bias. This is x1, this is x2. Then we will first implement the AND gate. Okay. So this is the linear summarizer for AND gate. So x1 is 1, x2 is 1, and we have the biases minus 1.5. Therefore, this is minus 1.5. Now we will implement the NOR gate, and NOR gate is this. Therefore, let me change the color. This is NOR gate, and this is minus 1. X2 is also minus 1, and the weight for bias is 0.5. Therefore, this is 0.5. Okay. Now we will take the OR of this. Therefore, let this be the linear summarizer for OR gate. From AND gate, we have a weight of 1. From NOR gate, we have a weight of 1. And the bias is C. It's minus 1. Therefore, this bias can be taken as minus 1. And this will be passed on to an activation function phi of k, which is the threshold function. And we will get the output y, which is the XNOR gate. Okay. Thus, we have successfully implemented the XOR gate and XNOR gate using McCulloch-Pitts model. Now, we will move on to the next topic, that is implementation of logic gates using Hebbian mechanism. Okay. Before going on to that, let's have a quick glance on how weights were updated in Hebbian mechanism. So, in Hebbian mechanism, we have delta w kj of n equal to eta into xj of n into yk of n. Remember? And we had wkj of n plus 1 equal to wkj of n plus delta wkj of n. So I hope that everyone remembers this part, or else please watch the previous video on Hebbian mechanisms. Okay. Now coming to the implementation part, initially we will take all the weights, that is all wkjs as 0 only. Now let the input vectors be given by xn bar equal to x1 bar, x2 bar, etc. to xn bar. Okay. And the corresponding output vectors y bar equal to y1, y2, etc. to yn. Okay. Now each of the input vectors may have multiple inputs like x1, x2, etc. Okay. And also the output can also be in similar way, that is each output vector can have multiple outputs like y1, y2, etc. to ym. Okay. Now in order to find delta wkj of n, what we do is we will take the vector product of xi bar into yi bar. Note that this xi bar is the input vector, okay, not the individual inputs, okay. And this eta is either given in the question, or if it is not given in the question, we can take eta as 1, okay. After this, we will update the weight such that wkj of n plus 1 is equal to wkj of n plus delta wkj. Okay. So this is the manner in which you need to proceed, and you need to repeat these steps until we have taken all the input and output pairs. Okay. Now let us move to the first question, that is implementation of logic AND gate using Hebb mechanism. See, this is the truth table for AND gate. Note that instead of 0, we have written as minus 1. Why? Because if it was 0, then when we try to update the weight, this xj term will become 0. Therefore, the updated weight or the change in weight delta wkj will be 0. In order to tackle that problem, we had written minus 1 instead of 0. Therefore, 1 into 1 is 1, 1 into minus 1 is minus 1, because 1 into 0 was 0, right? And minus 1 into 1 is minus 1, and minus 1 into minus 1 is minus 1. Now we are also given with a bias, and note that bias is also an input in the neuron model we have discussed, right? Therefore, we will try to implement the steps. So, proceeding in the manner we have discussed earlier, delta wkj of 0. Wait, see, since we are given the input vector starting with x1, let's name it as 1. Okay, instead of 0, I am naming it as 1 is equal to, and we are not provided with eta, so we are taking eta as 1 into the first vector is x1. Therefore, 1, 1, 1. See, these are the three inputs for the first input vector, right? And we have output vector as y equal to 1. Therefore, this is 1. And we get it as 1, 1, 1. Now, we will try to update the weights. That is, wkj of 2 is equal to wkj of 1 plus delta wkj of 1. See, I have already told you that the initial weights are always taken as 0. Therefore, this is a 0 vector. 0, 0. Okay. Therefore, this is 0, 0, 0 plus 1, 1, 1. See, delta wkj is taken as 1, right? Therefore, we get it as 1, 1, 1. Now, we will move on to the second input-output pair. Therefore, delta wkj of 2 is equal to, input vector is x2 equal to 1, minus 1, 1, and we have eta as 1, and the output vector is minus 1. Therefore, minus 1, we can write as minus 1, 1, minus 1. Therefore, wkj of 3 can be written as wkj of 2 plus delta wkj of 2, which is 1, 1, 1, see from here, plus minus 1, 1, minus 1, which can be written as 0, 2, 0, right? Now, we will move on to the third input-output pair. Therefore, delta wkj of 3 can be given as, the learning parameter is 1 into input vector x3 is minus 1, 1, 1, and the output is minus 1. Therefore, minus 1, which can be written as 1, minus 1, minus 1, right? Therefore, wkj of 4 can be given as wkj of 3 plus delta wkj of 3, and delta wkj of 3 is this. Therefore, adding these and this, we will get it as 1, 1, and minus 1, right? Now, moving on to the fourth input-output pair, we will write it as delta wkj of 4 equal to learning parameter, that is 1, into minus 1, minus 1, 1. See, the inputs are minus 1, and 1, and the output is minus 1. Therefore, into minus 1, which can be written as 1, 1, and minus 1. And we can write wkj of 5 is equal to wkj of 4 plus delta wkj of 4. And we have wkj of 4 as, see, this 1, 1, and minus 1. Therefore, 1, 1, and minus 1 plus, we have found delta wkj of 4 as 1, 1, minus 1. Therefore, 1, 1, and minus 1, which can be written as 2, 2, and minus 2. So, for the implementation of logical AND gate using Hebbian mechanism, we have the final weight of the system as W11 as 2, W12 as 2, and W13 as minus 2, where the inputs are x1, x2, and x3, where x3 is the bias, okay, and the output is y1, right? Thus, we have implemented the AND gate. Now, we will move on to the OR gate, okay. And before moving on to the OR gate, it's a better thing if you pause the video and implement it yourself, okay. Okay, now we will implement the logical OR gate. In the similar fashion as before, we will take the initial weights as wkj equal to 0, 0, 0. Then, for the first input-output pair, we have delta wkj of 1 as, since the learning parameter eta is not given, we will take it as 1, into first input, that is 1 1 1, and I hope that everyone is familiar with this notation, that is instead of 0 we are using -1. Okay, and the output is 1, which can be written as 1 1 1, and we can write wkj of 2 as delta wkj of 1 plus wkj of 1, right? Therefore delta wkj of 1 is 0. Therefore 0 0 0 plus 1 1 1, which is nothing but 1 1 1. Now we'll move on to the second input output pair. Therefore delta wkj of 2 can be written as eta is 1, and the input vector is 1 minus 1 1, and the output is 1, which can be written as 1 minus 1 1, and we have wkj of 3 as wkj of 2 plus delta wkj of 2, which is 1 1 1 plus 1 minus 1 1, which can be written as 2 0 2, right? Now moving on to the third part, we can write delta wkj of 3 as 1 into input vector is -1 1 1 -1 1 1, and the output is 1. Therefore -1 1 1. Therefore we can write wkj of 4 as delta wkj of 3 plus wkj of 3, and wkj of 3 is 202. Therefore 2 0 2, and delta wkj of 3 is -1 1 1. Therefore -1 1 1, which can be written as 1 1 and 3. Now moving on to the fourth input output pair, we can write it as delta wkj of 4 as the input vector is -1 -1 1 -1 -1 and 1, and the output vector is -1. Therefore this is -1, and we get the output as 1 1 and -1. Now we can write wkj of 5 as wkj of 4 plus delta wkj of 4, and we have wkj of 4 as 1 1 3. Therefore 1 1 3, and delta wkj of 4 as 1 1 and -1, right? This can be written as 2 2 and 2. Therefore the final Hebbian network, the final modified weights are w11 equal to 2, w12 equal to 2, and w13 equal to 2. So we have implemented the logical OR gate for Hebbian mechanism. Okay. Now in similar fashion, try to implement the NOT gate also. In case of NOT gate, we get the input output as, we can take the input vector x1 as 1, bias is taken as 1, and the output vector will be 0, right? And in NOT gate, whenever the input vector is high, we get the output as low. Therefore this should be 0, but as stated before, we will be taking as -1, and the second input vector will be -1, bias as always will be 1, and this will be 1. Okay, the only thing you need to take care is that do not take 0 anywhere. Take -1 instead of 0, because of the reason I have told you before. Okay, now another very important thing you need to notice that we cannot implement XOR gate using Hebbian mechanism. The reason is that the XOR gate inputs are not linearly separable. Okay, let me explain this to you by plotting the XOR gate inputs to a graph. Okay, therefore let this be the first input, let this be the second input, let this be 1, and let this be 1, and this point is 0. So we know the XOR gate inputs as x1 x2 y 0 0 0 1 1 0 1 1, and the outputs as 0 1 1 0. So whenever one of the input is high, we get the output as high. Let me plot this. So in this case it is 1 1, and when it is 1 1, we have input as 0, and let me use the red color to plot the 0 outputs. Okay, so when the input is 0 0, also the output is 0. Therefore this point is also right. Now let me use the green color to plot the outputs when it is 1. Therefore when it is 0 1, the output is 1, and when it is 1 0, the output is 1. Now you can see that there is no way to separate the ones and zeros using a single line, that is to separate the greens and reds using a single line. Wait, let me draw the input graph for AND gate also, so it will be more clear. So let this be x1, let this be x2, and this is 1 and this is 1, and we are drawing for AND gate. Okay, this is for AND gate. So as usual we will use the green color for ones, and AND gate is 1 only when both inputs are 1, right? Therefore this is green and all other points are red, right? Now in this case we are able to separate the greens and reds, that is ones and zeros, using a line, right? See, this line will separate all the zeros to one side and all the greens to other side. In similar fashion, we are not able to draw a line in this graph, right? That is the problem with XOR gate. That is, it is not linearly separable, and we can use Hebbian mechanism only for linearly separable inputs. Okay. Therefore, it is an important criteria to check whether the inputs are linearly separable before proceeding to implement the Hebbian mechanism. Okay. Otherwise, all the answers you get will be void, because it is impossible to implement a Hebbian mechanism for that input, right? So always keep this note in mind while doing a question based on Hebbian mechanism. Okay. I hope that everyone understood the concepts in this video. And if you have any doubts, please do ask in the comment section. Okay. Thanks for watching. Have a good day.